Today we're going to be speaking about Wrangling with a Ghost, which is essentially an inside story about how Spectre and Meltdown was mitigated within Microsoft. Yesterday there was a panel about the industry cooperation in mitigating Spectre and Meltdown, which was really interesting. Also today there is a talk in the last slot about Meltdown. If you're interested in technical details on Meltdown, that is probably the better talk to go to, because we're going to talk mostly about mitigation. We're going to skip relatively quickly over the attacks. That also makes our talk kind of orthogonal to the two other Spectre and Meltdown talks that have been here on the past. So Spectre and Meltdown won 2 ponies yesterday, so we kind of think that it's a relevant talk. So without further ado, my name is Anders Fogh. I am a security researcher. And I should mention here that I did this research while I was employed by GData Advanced Analytics and while under contract with Microsoft. The presentation here does not reflect the views of my previous nor my current employer.
And I'm Christopher Ertel. I'm a security engineer in the MSRC in the UK office. All right, so Spectre and Meltdown. These issues gained a huge amount of interest from the research community when they were first disclosed earlier this year, because they represent a fundamentally new class of hardware vulnerability, which is an extremely rare occurrence. And the scope of the impact is just massive, potentially leaking information across nearly every security boundary that we rely on. So when we were first made aware of these issues in June last year, we kicked off our CERT incident response process. And this is the typical process that Microsoft follows whenever we're made aware of a security vulnerability either being actively exploited in the wild or just a high threat risk that requires mobilizing a large number of people within Microsoft. In particular, for Spectre, we realized we were dealing with a fundamentally new class of vulnerability, and so we decided to bring in an expert, Anders. So once again, why does Microsoft care about these issues? Because they are relevant to nearly every security boundary we rely on. So if an attacker has some kind of code execution, even within a scripting environment such as JavaScript, they might potentially be able to leak information across a security boundary. So this affects potentially Hyper-V, Windows kernel, and the browser.
So before one can actually start mitigating a new class of vulnerabilities, one has to think about what are these vulnerabilities, especially when it's a new class. And what we did was we made a taxonomy and a framework to reason about not only the attacks, but also how the mitigation could look like. And this is going to be the topic of this section of the talk. But before we can get that far, we need to talk a little bit about how modern CPUs actually work, just for context. So usually we think of programs as recipes that execute one instruction after the other sequentially. And in fact, this is how programmers usually try to write their programs. It turns out that if the CPU interpreted the program in that same way, it would be rather slow. So modern CPUs, especially the high performance general CPUs, do many things at the same time. And this takes in a couple of different ways. The first way is pipelining. Pipelining means that when it takes an instruction in, it works on this instruction, doing bits and parts of it through multiple stages, essentially like an assembly line. The second thing is modern CPUs are superscalar. That means nothing more than they're capable of working on more instructions than one at the same time. And we'll take a look about how that works in a second. And then we have out-of-order execution. So out-of-order execution means that the instructions are no longer treated like a recipe. They are actually executed when the dependencies resolve and when resources are available. So this makes it possible to execute things out of order, and this again is a speed optimization. Finally, we're going to talk about speculative execution as well. And speculative execution is essentially when the pipeline is working on data that is predicted instead of actually calculated. We'll also be talking a lot about that. So here you see a very small assembler program that consists of 2 mov instructions and an add instruction. The first and the third instruction here don't have any dependencies, which means that if we want to start to run this program on a CPU, both instructions are ready to start running at any time. Whereas the middle instruction depends on the result from the first, which means that this is not ready, it has to wait for the first instruction. So when we actually start executing this program on a modern CPU, we'll have that the first and the third instruction will start executing. This is both super scalar, because we're executing two instructions at once, and it is also out of order, because the third instruction shouldn't execute in recipe order until the second instruction actually was done. The advantage of doing it this way is that since we're executing two instructions at once, this program will take the time of one mov and one add, whereas if we were executing in a program order, recipe order, it would be the time of two movs and one add, which is, of course, a lot more. So, about speculation. When we went into this, we made a very general definition of what speculation is. More general than you'll normally find in textbooks. So our definition of speculative execution was that it's speculative whenever the pipeline is working with data that may turn out to be wrong, that is predicted in some kind of way. So why does CPU predict data? Well, typically it's because real data arrives late, they're calculated later in the process, and that they can be predicted very well. So if you get this situation, instead of waiting for the data, you can predict it. If you predict it correctly, you win. If you predict it wrongly, you unroll. So speculative execution consists of many kind of things. You can speculate on, say, conditional logic. You can speculate on the instruction pointer where that has to go. You can speculate on the values of registers. You can defer error handling, things like this. So when misprediction is actually unrolled, all the results that comes from working with the mispredicted data are just dropped, just completely removed from the CPU. And this includes registers, memory operations, things like that. And when these things are then dropped, execution will pick up where the prediction was made, because now we have the right data. However, there is this tiny snack here. Not everything is rolled back, and an example of what's not rolled back when speculative execution is unrolled is the caches. So speculative execution can actually load a cache and will not unload it afterwards. So we need to talk a bit about memory uses and caches. So it turns out that main memory, that is DRAM modules, reading data from those are really, really slow compared to how fast a modern CPU actually is. And one should also notice here that memory access patterns are not random. They can, in terms, be predicted in some way. And the way that this works is that usually CPUs tend to use the same memory again and again. And there's a solution for CPU designers to this to make this faster. And this is to make a very small cache inside of the CPU, not as part of main memory, but inside the CPU, and keep the most recent memory access in there and serve memory requests from this cache if possible. And this, of course, makes it a lot faster. So this also entails a side channel. So an attacker can time how fast a memory access is, and if it's fast, well, it was recently used. And this, of course, means that he is able to tell something about memory access patterns made by whoever executed before him, which, again, means he's able to tell something about that. And we're going to see this a lot going through this presentation. So the fundamental idea about Spectre and Meltdown is that when the CPU unrolls speculative execution, it doesn't unroll everything. The cache is the example here. And that through this side channel, we're capable of recovering information that was used during the speculative execution. And the results here can then be recovered through the side channel. And in some cases, these results contain private data, and we have leakage of private data between security domains. So moving on to Spectre variant 1. So Spectre variant 1 works with prediction of conditional branches. So the thing about a conditional branch is that you don't know where it goes until it has been executed. However, we want the pipeline to be full, to have it full of instructions to work on from the out-of-order execution engine. For this reason, the CPU predicts the conditional branches because it can do that right up at the top of the pipeline and keep on filling the rest of the pipeline. So we have this delay here that I was talking about before. This actually works quite well. Modern CPUs are capable of predicting conditional branches above 99% of the times correctly. However, we said before that conditional branches are predicted on past history of the CPU. And this is a problem because if an attacker is running on the CPU, he actually determines past behavior and he determines how these things will be predicted. And this allows the attacker to determine the prediction. And if we look at the code below the blue thing, we'll see what essentially will be a conditional branch. And we have an untrusted index in here. So if the prediction is wrong, or no matter what the value of the untrusted index, with the wrong prediction, the code below the if statement can execute speculatively. So this means that the second line of the code is capable of accessing in a buffer indexed on our untrusted index. And this untrusted index can take any value, meaning that we essentially have arbitrary load of memory into the CPU. This is in and of itself not a big problem. The problem comes with the search statement, and the search statement is essentially loading into the cache some address depending on the value that we read from arbitrary memory. So we taint the cache in a way that discloses what the value of the memory, the arbitrary memory that we read in the previous statement. In other words, we're capable of reading arbitrary memory using the side channel timing attack we described under the caches. So if you're wondering what the 40 in that statement is, it's because caches don't really work on bytes. They work on blocks of 64 bytes, and 40 hex is 64 bytes. And to be able to distinguish between all different values, you need to multiply by that. The consequence of having this code somewhere in your computer is that if an attacker can execute this code, can find, execute, or generate and execute this code, he'll be able to read memory at the privilege level where he found this code. So if this is a kernel or the hypervisor or an enclave, doesn't matter, he's capable of reading the memory with a higher privilege. This is a clear violation of basic security principles. So moving on to Spectre variant 2. This time around, it's not conditional branches, it's indirect branches. And indirect branches is not predicted whether they are taken or not taken, because they are always taken. They are predicted where they are going to go. So, like before, indirect branches can be trained. But there is a special thing about indirect branches is that it's not just a single bit that has to be predicted, it's an entire address. And for this reason, the CPU keeps a table where any indirect branch's past behavior is stored. This is called the branch target buffer, or BTB. And because you can't have a table for every possible indirect jump, it actually is indexed with just a subset of the bit of the address of the indirect jump. This means that if an attacker knows which bit this is, and this can be reverse engineered and has been reverse engineered, he can just allocate a piece of memory, put an indirect branch in a location that collides with this, and then he can start training his indirect branch to go wherever he likes. Meaning that an attacker is capable of picking code in the security domain where he found the indirect branch, essentially anywhere. So I tried to illustrate this here with the red 5000 Rx equals that. It should go to 5000, but speculatively it can go anywhere, and an attacker can make it go to 4141 if he likes. The assembler code on the lower part of the slide is the same as the C code in the previous slide. It just reads memory and persists it into the cache. So this makes the attack a lot worse from a defender perspective, because now we don't need to have a long block of consistent code. We can actually just have an indirect branch and the rest of the code that an attacker needs somewhere, which is of course much more flexible. Again, the consequences of this is an attacker is capable of reading memory that he shouldn't be able to read, that is in the security domain where he finds these two things. Which leads us on to the third variant. The third variant is also known as Meltdown. And it is fundamentally different from Spectre in that perspective. You don't need to find or create this code. You can bring it with you. An attacker can write all the code that is needed for this attack. So this is the first major difference. The second major difference is that this is not about branches. So what happens here is that when a user tries to access kernel memory, the kernel says, no, you're not allowed to do this. It throws an exception and stops program execution, which is great because then you can't read kernel memory. Except what happens on some CPUs is that when you try to read kernel memory, the CPU speculates, oh, he's just reading some memory, I should give it to him. And at some point later, it will discover, oh, there should be an exception. And this gives an attacker a window to do the exact same trick as before, persist the memory into the cache and side channel it out afterwards. And this leads to the situation where an unprivileged user is capable of reading arbitrary kernel mode memory, and that again is a clear violation of standard operating system security. So now that we have seen the three variants that we were presented with in June last year, we go on to building a taxonomy about that. The first question we need to raise is, why do we want to create a taxonomy? The thing is, when you design mitigations, especially mitigations which comes with a new class of vulnerabilities, you want to be systematic about it. You don't want to mitigate the three examples that we were sent from Google Project Zero. You want to mitigate every possible variation of these. And to do this, you need a taxonomy to reason about how this thing actually works. When does it break down? When doesn't it break down? So we went on to work on a taxonomy. And what we noticed was that there are 4 steps that are required for an attacker to run a speculative execution attack. The first thing that an attacker needs to do, he needs to get wrong data into the pipeline. And we call the process gaining speculation, and we call the primitive the code that actually does this, that for Spectre he'll need to find, for Meltdown he'll need to write. We call this a speculation primitive, and this essentially gets wrong data into the pipeline. The second thing that an attacker needs to make sure is that once he is in speculation, the CPU will try to rectify this as soon as possible. And he wants to delay that so that he can run the code that persists the secret data into the cache or somewhere else to make sure that he can read it out later. So there's a race condition here, and he needs to make sure that he can win that. And we talk about a window for speculative execution, and hence we're talking about Windows gadgets. And the third step he needs to do is he actually needs to write the secret into a side channel where he can read it later. We call this disclosure gadget. And finally, he needs to get the information back from the cache or wherever he stored it, in whatever side channel he used, and we call this the disclosure primitive. This is where he gets the data back so he's able to work with it and disclose it or do whatever he wants to do with it. So it should be fairly obvious that if any of these steps breaks, there is no speculative attack. And when you think of it like this is very important information for somebody who wants to mitigate this stuff. I'm taking a closer look at some of these things. So gaining speculation, the speculation primitive, essentially we have 3 versions, we have 3 versions of it. We have misprediction on conditional branches, we have misprediction on indirect branches, both of which could be trained. The indirect branch is a bit more sophisticated, there allows an attacker more possibilities. And finally we have the meltdown version, where we have an interrupt that is delivered after it should be, and allows execution to be continued with data that shouldn't be present in the pipeline. So the second is window gadgets, maintaining speculations. The thing here is that once an attacker execute the speculation gadget, he is on a race condition against the CPU, finding out that it was working on predicted data, mispredicted data. And to win this race condition, he needs to have some code that gives him time. And he also needs to make sure that the code he actually wants to execute can execute out of order. So there are some limits about how the code that generates the windows has to look. And window gadgets can occur naturally. That is kind of the entire point why the CPU is able to do out of order execution. But in some circumstances, there are some ways that an attacker can actually engineer having good window gadgets. And the actual window size is very difficult to reason about because it derives from a lot of things. The first is the actual hardware on which it's running. The second is how the dependencies of the code looks like. And the third is what other congestions are happening on the CPU at the time that it's running. So it's kind of difficult, but you can, in big terms, reason about what kind of windows you're looking at. The third gadget that we need is the disclosure gadget. And the disclosure gadget is essentially just writing into a side channel. And the example here is the cache that we had before. And it needs to run within the speculative window. And the fourth and final is, of course, getting the data back from wherever we stored it before, using some kind of primitive. We call it the disclosure primitive. And we can generalize a bit more about that, but let's go into specific instead. So taking each of the four components with examples, we had it before, conditional branches, indirect branches, and deferred into interrupts is the techniques that we knew on June. And when we go on to window gadgets, we have a couple of special cases. The first case here is when we have dependencies on a loading something from memory. So this is the case where the attacker is actually capable of engineering the gadget. So if he makes sure that the value here in P is not in the cache, it will load much, much slower than if it were. And this actually increases his window size if there's a dependency on this value. And in this fashion, he can create a window for himself. So something like this is likely to occur naturally in code, and he can then engineer a situation where his window gets big enough. You can take this to an extreme. So if you have a chain independent loads from uncached memory, you can create very large windows up to the theoretical limit that is determined by the hardware. That, however, is not very likely to be present in much naturally occurring code. And the final thing is a bit more worrying in natural occurring code. This is because if you have integer operations on the same variable, that too can cause a window to be created. And that is something that is likely to occur in natural occurring code, meaning that it's likely to find gadgets, window gadgets, in natural occurring codes just by having somebody do something on whatever integer or even floating point. So, of course, there can be more window gadgets than the ones I listed here. In fact, there could be an infinite number of them. But we have an idea about how they could look like. The next step is the disclosure gadget. We talked about two levels of indirections a lot so far, because getting arbitrary memory, persisting the arbitrary memory into the cache. This is the second one in the box here. But it's easy to realize that if, say, you have some secret value X that is used in speculative execution and you do a load on that, you'll load the cache for that as well. And this means you have another disclosure gadget with just one level of indirection. And you can do 3 levels of indirection as well, and that will leak memory too. And you can probably do a lot of other things that will write something into some side channel. And this is important to notice when you want to do mitigations, because it becomes more than just the case that we had before in the examples that we got from Project Zero. And finally, we have the disclosure primitive. Here we're just listing disclosure primitive that relates to the cache, because that is what we have been doing in this talk. So we have the classic flush and reload. The flush and reload, that is essentially what I've described so far, requires that the attacker and the victim code actually share some memory. That is not a strict requirement. There are other attacks on the cache called evict and time, and there is prime and probe, which don't have this requirement, which can leak data without actually sharing memory with the attacker, between attacker and victim. If you want to know more about these two attacks, I did a talk at Hack in the Box in 2016 that covered these kind of attacks in much more detail. So once we have a taxonomy in place, we need to look at where are these scenarios relevant. So the first thing that we did was we came up with some categories of disclosure. And the first category is what happened inside a virtualized system. This is relevant for things like Azure, for Hyper-V, and this is like disclosure between two guests, or disclosure of memory between the hypervisor itself and a process. We have another category about what happens in an operating system, and here we're talking about disclosure from kernel, between processes. And we've had a final category about enclaves, and enclaves are sensitive because they're supposed to be secured against anybody in any scenario. And then we had listed all the scenarios that we could find. I'm not going to read them. And realized that Spectre version 1 and version 2 actually is relevant for everything here, whereas the Meltdown appears to be only relevant for operating systems and only between the kernel and the user. And that leaves the systematization part of this talk.
Thank you. So now we can begin to reason about the kind of mitigations we can put in place for these types of attacks. So we defined 3 mitigation tactics, the first of which is preventing speculation techniques. And specifically what we mean by this is we want to prevent unsafe speculation, where the speculation primitive could lead to a disclosure gadget. The second tactic we have is removing sensitive content from memory. So the idea here is to eliminate entire attack scenarios, or simply limit the severity of what a speculative read could actually disclose. And the final tactic we had was removing observation channels. So the idea here is to make it as difficult as possible, or even impossible, for an attacker to observe changes to the cache state, for example, and infer secrets from that. But the key point here is there's no silver bullet. For each of the attack scenarios, we require a different combination of mitigations, both hardware and software. Okay, so starting with removing speculation techniques, once more, the goal here is to prevent unsafe speculation, which could lead to a disclosure gadget. First thing we can do is have some kind of serialization of the instruction pipeline. So on x86, we have the lfence instruction, which has the neat property of acting as a speculation barrier. So if we think back to this variant 1 code pattern, we can use the lfence after performing the bounds check, and this will create the guarantee that speculation won't be able to continue on from past this point where untrusted index is greater than or equal to length. Second thing we can do is have some kind of implicit serialization. So thinking back to variant 1 again, we can use a conditional move instruction to set untrusted index to a zeroed register if it is greater than or equal to length, and this will force the misspeculated path to execute the subsequent 2 array operations with untrusted index being 0, which won't disclose a sensitive secret. And to do this, we have the qspectre command line flag in Visual C++, which will automatically detect potentially vulnerable code patterns and insert appropriate serialization. Similarly, for Microsoft Edge, we have mitigations in the Chakra JavaScript engine, which prevent an attacker from being able to create these kind of vulnerable code patterns to disclose memory. The next thing we can do is have some kind of workload isolation. So as we heard earlier, indirect branches are predicted based on past behavior, which is stored in the branch target buffer. These kind of prediction states are generally either shared per core or per hyperthread in the case of simultaneous multi-threading is enabled. So what we can do is we can assign a certain core to a guest VM, for example, and leave the others for the host. And what this will do is it will prevent a malicious guest from being able to collide the branch prediction state and trigger unsafe speculation from an indirect branch on the host. And to do this, Hyper-V supports min-root and CPU groups, which can be used to schedule the behavior of the guest. The next thing we can do is make use of the indirect branch control features, which are provided by the microcode updates by Intel and AMD. So we have three new options. We have IBRS, which kind of acts as a way of creating two different privilege domains. So we set IBRS to 0 for the lower privilege state, and then on transition into the higher privilege state, such as on kernel entry, we can set IBRS to 1. And this will create the guarantee that the higher privileged state will not be influenced by prediction changes made by the less privileged context. Next thing we have is IBPB, which essentially allows the operating system to flush this prediction state. So this might be used when switching contexts, switching processes, or switching guest virtual machines for the hypervisor scenario. And the final thing we have is STIBP. So as we saw, in the case where simultaneous multi-threading is enabled, two co-located threads on a single core might share some prediction state. So if we have a higher privileged context running and a lower privileged context running on the same core, the lower privileged context might be able to collide the branch prediction state. So setting STIBP to 1 just prevents this attack scenario. And all versions of Windows client that are supported make use of these features. The next thing we can do to prevent speculation techniques is use non-speculated or safely speculated indirect jumps. So on Intel CPUs, the far jump and far ret instructions, which are indirect jumps that also change the code segment, will not be speculated. So we can replace indirect branches with these instructions, and this will guarantee that misspeculation will never occur from an indirect branch. Similarly, for AMD CPUs, we can use the LFence instruction, and this will guarantee also that misspeculation will never occur from an indirect branch. There was also this proposal by Google for retpoline, and this essentially can be used to control speculation after an indirect branch. So speculation could go to an infinite loop, say, whereas architecturally the jump will resolve as normal. And Windows kernel and Hyper-V are using a combination of these to best optimize performance. So moving on to the second tactic, removing sensitive content from memory. Once more, the goal here is to limit the sensitivity of memory that speculation could read and disclose. The first thing we can do is have hypervisor address space segregation. So as the hypervisor runs, we can map guest physical memory on demand as it's required, as opposed to historically where the hypervisor would have all guest physical memory mapped at all times. And so what this means is that if a malicious VM performs a hypercall and tries to induce unsafe speculation, it will only ever have access to its own guest physical memory, and so it will not be able to disclose guest physical memory from other virtual machines running on the host. The next thing we have, this is specific to variant 3, the kernel to user information disclosure scenario, is KVA shadow. So previously in user mode execution, the kernel page table entries would be mapped but just marked as inaccessible. With KVA shadow, we guarantee that user mode execution only ever has access to its own page tables, and we add the kernel page tables back in when we transition to the kernel as needed. All supported versions of Windows client enable this by default. And the final tactic, removing observation channels. Once more, the goal here is to make it difficult for an attacker, or even impossible, to observe changes to the cache state and infer secrets from that. So the first thing we have is mapping guest physical memory as uncacheable. So if we have some system physical memory, we can map it as write-back cache for the guest, so there'll be no performance impact for the guest itself. But for the hypervisor, we can map it as uncacheable. And what this will do is it will create the guarantee that if the hypervisor performs a speculative load on this guest physical memory, it will obey the uncacheable property, and so it won't be able to make any cache changes that will be observable to the guest through a flush and reload primitive. So this acts as a generic mitigation for guest to host flush and reload. The other thing we can do similarly to prevent guest to guest flush and reload disclosure primitive is simply ensure that we never share any physical memory between two guests. So we ensure they always have their own copy of everything, and this ensures that changes made to the cache in one guest cannot be observed by another through the flush and reload primitive, which requires shared cache lines. Finally, we can decrease the timer precision in the browser. So there's this API performance.now, which is accessible to JavaScript, which previously could be used to time a single load and then determine whether that address was in the cache or not. Now what we do is we decrease the precision of this timer, and we also add random jitter to prevent clock edging techniques, which makes it much more difficult for an attacker to perform a speculative attack in the browser. So for closing remarks, I just want to reiterate the point that there's a large number of attack scenarios, and for each of them we require a different combination of hardware and software mitigations to prevent the problem as best as possible. Thinking back to the variants themselves, variant 1, well, they're all hardware vulnerabilities. Variant 1 is going to require software changes, so that might be using the qspectre command line flag to insert appropriate serialization. Variant 2 is mitigated by the operating system by making use of the indirect branch controls, for example. And finally, variant 3 is completely mitigated with KVA shadow. So once more, userland execution never has kernel page table entries mapped. Since then, we've received also some new variants, which I'd just like to go over briefly. The first of which is speculative store bypass, which worked by creating mispredictions between data dependencies of store and load instructions. The mitigation for this is the same as variant 1, just adding serialization to the pipeline for vulnerable code patterns. Alternatively, there is a feature of the CPU which can be used to disable this memory disambiguation optimization. But that is disabled by default, as no vulnerable code patterns have been found affecting Microsoft code. The second of which is the lazy floating point state restore. So 32-bit versions of Windows prior to 10 would make this optimization where, when context switching between processes, instead of always just copying the floating point registers, they would simply mark them as inaccessible and then restore them on first use through triggering an exception. The problem with this was speculative execution could read stale floating point register values from a prior process, as the exception could be deferred, similar to variant 3. The mitigation for this is simply to disable this optimization, which is done in the latest version of all Windows 10. For bounds check bypass store, this was where a conditional branch would mispredict, leading to an out of bounds write speculatively. And if this speculative out of bounds write corrupted an indirect branch target, this could lead to speculation at an arbitrary attacker controlled address, if that was then called, similar to how variant 2 worked. So that's powerful because it could lead to a disclosure primitive. The mitigation for this is, once again, identifying vulnerable code patterns and inserting appropriate serialization. Then moving on to, finally, NetSpectre, which was the first attack demonstrated over the network. The mitigation for this is, once more, just detecting vulnerable code patterns and inserting serialization. But we expect this to be a continuing subject of research, and so we've launched our speculative execution side channel bounty. The max payout for this is 250K USD for new variants. We also have more information about the variants themselves and developer guidelines on our TechNet blog. So I'd just like to finish by saying thank you to everyone who is involved in this research and the mitigations. It's been a tremendous undertaking.
I would like to join in that thanks, and I would also like to thank Microsoft for allowing me to be a part of that process and for allowing me to be here today. And of course, to all of you guys who came to watch this talk, thank you very much.